Great. Okay, we're rolling. Good. Yeah, let's make a slow start. Everyone know you're responsible for finishing quiz number 1 before Friday. So do that. Josh is going to join us next Monday online, and we're going to talk through statistics and what people do well, what people didn't, and you guys can ask us questions. So, yeah, I'm happy to take my mask off if people prefer me to, but the condition is everybody else wears a mask. So, anyway, so, and assignment 1 is due in less than 2 weeks. Turns out this is very, yeah, coming up quite soon, and it's a lot more work than the quiz. Hope you're enjoying the work so far. And there has been a healthy amount of piazza activity, and Josh has been helping to fill a lot of them. Thanks. So that's the housekeeping items for today. And this is what we're going to really talk about today. It's a bit different. I thought, well, since we're doing the in-person lecture, which is different, so we might as well talk about something that's a bit outside of the book. The alternative would be to talk to you guys about neural networks, lecture number 1, which I thought, yeah, we can do something different. And there are good reasons to choose to talk about generalization because they are the theory and the foundations of why machine learning works, which I think are very exciting as a topic. So we kind of all know from different exposures to machine learning practically that, well, if I train my neural net or whichever machine it is on a chunk of data, it seemed to work okay, but why exactly, right? So the high level question that we are going to try and answer today is why learning works. What we are not going to be able to answer formally today is why overparameterization works, why giant and deep neural network works. But we're going to give you a cultural exposure on the empirical side of this. Basically, what people have observed. So I would say that the theory on overparameterization is still evolving. And there's some pointers to read for you guys. And the content of today mainly comes from what's called I call it ML storybook. It has a formal title, patterns, classification, and so on. ML story is simpler. It's written by 2 very well-respected active researchers in this field, Moritz Hart and Benjamin Rick. So they were both at Berkeley. Moritz Hart recently moved to Germany, Tübingen. The focus of Benjamin's research is optimization, and Moritz works on optimization and also fairness and accountability of machine learning algorithms recently. So I would say the content is definitely fresh. There are since we talk about this in Canberra, as usual, I try to highlight local researchers or people who has had a connection with ANU, who have contributed to this area of research in general, right? So for example, Peter Bartlett, another professor in Berkeley, have done quite a lot of work in this area on generalization and most recently generalization of neural networks. He spent more than 10 years in the ANU as academics and all the way until professor. You can read his bio. Another person was highlighting Bob Williamson, who was until recently at the ANU for 30 years. He's also now at Germany. He has done a lot of fairly foundational work on different kinds of loss functions, how we think about loss functions, as we will see in a bit. So this lecture, here's a warning. It's a bit notation heavy. There are different concepts to grapple with. The essential math is not that hard, right? So just bear with each other and ask me questions. So yeah, I will keep an eye on the chat for people online who have questions. And people here can just raise your hand or interrupt me. And if Josh could, you can keep an eye on the chat and fill questions and just shout at me. That would be nice. So let's start with some notations first. Our predictor, right? So, okay, the input to the trained machine learning algorithm is called X. The label, training label is called Y. Target is called Y. The predictor is f of X. And we compute some sort of distortion metric between f of X and Y. So that's our loss function. So we read the notation inside out, right? The outer layer is the expectation, right? As usual, expectation is just a symbol. It doesn't exactly tell you what to take expectations over. In this particular case, it is over the true data distribution X comma Y, the joint distribution X and Y. We usually don't have access to this. Just like what we discussed in the bias variance part of the regression lecture, a lot of these are sought thinking tools. Right? So for now, we assume that we have access to an infinite amount of large samples to the data. Then we can use this to think about generalization. And this expected loss over the true data distribution is called risk. This might not be the most intuitive name, but we just have to remember it for this class in the lecture. So risk of a predictor is its expected loss over true data distributions. So there are some simplified or stretched notations. So in here we compute loss of f of big X, which is a collection. We can also compute the loss over one sample, one data point, small x comma y. Right, and the two arguments are just written as one of them is the predictor, the other one is the data tuple. We sometimes also write this because the predictor f is often parameterized by vector w. Right. Now, if we have a sample, a data set, basically, it's basically a sample from the data and target joint space. It's a list of all the tuples, and what's called the empirical risk for the sample is basically the loss function over each individual data tuple, and summed over the I from 1 to n data points. Right, easy enough. Here's the term that will reappear a lot in this lecture. It's called empirical risk minimission. It's a fancy name for training, basically. What it does is, over the space of the functions that we parameterize to learn, we seek to find the optimal predictor f star in the specified function class curly f. That minimizes this risk over this particular training sample. Right, so what this does is essentially minimizing training error and training loss. And after minimizing that, we get the optimal empirical risk R sub S F star. So it's just a fancy name for training so far. Ideally, we will want the loss on scenes examples to approximate the loss on unseen examples. So this is why we expect machine learning to work. Practically, we expect the empirical risk, the training error we get, to be sort of smaller than the generalization error or error on the test data. And we've seen this a lot. You guys have worked on learning curves and you know this. So therefore, we define the generalization gap of a predictor F with respect to data set S. Okay, that's a mouthful. It's basically risk of the true expected loss of a predictor F minus the empirical on data sample S. So we call this delta gen of that. Right. Right. So the generalization error is basically, or the risk, the true risk, is basically the training risk plus this delta gen. If you're training a super huge, deep, overparameterized neural net, a lot of times, like, we can manage to make the empirical risk small enough through optimization or SGD done right. Most of this class and other machine learning classes focus on getting us to think about how to do that. What are the classes of small f or curly f, and how do we optimize the training risk, right? Then all that remains is to worry about is generalization gap. So far we've done no new math. We were just like defining a bunch of concepts that are essentially known to us already. Right. So just hold on a bit, and then the generalization gap will appear. Yeah, you say why? Like how does how does generalization gap behave and so on? We'll get to that, right? So before that, let's take a detour to the modern practice of machine, namely overparameterization. Here's the traditional view that we start with, right? In the textbook, you see versions of this. Well, no, that our textbook is written before, let's say, the revival of like neural networks. So the traditional view is that there is a sweet spot in the complexity of your model within the model class. You think the number of polynomial coefficients and things like that, right? So the empirical risk, the idea is that if as we make the model more and more complex, the empirical risk gets driven down. Basically, we can try and feed the data better and better with more and more parameters, roughly speaking. But the true risk decreases and then rises. And on the right-hand side, what we usually say, hey, overfitting occurred. And we're fitting on the noise rather than the data patterns. And furthermore, people have actually tried to capture this phenomena quite like precisely, right? So here are two formulas that we didn't quite cover in our class, but they appear in the PRML book. One is called BIC, Bayesian Information Criteria, which is like the log probability of data is roughly the data likelihood minus, like, or the data likelihood is penalized by the model size, M, and also amount of data we have, log of N. And this -1 version is the simpler version of that. I forgot whether this one is called the AIC or not. You get the idea. So the old theory is overparameterization is bad and should be. The evidence from recent machine learning practice, however, have pointed to this phenomena that's nicknamed double descent, or actually formally named double descent by a number of academic papers. What it does, the phenomena in a like cartoon-ish picture looks like this. Basically, what we saw in the old theory is the left-hand side. The generalization error rises when we have more parameters, but after a certain point, it starts to drop again. So this is quite a bit perplexing, but also fascinating, right? So what we saw before was only the left-hand side of this picture. It says complex models over here, they can simultaneously achieve close to zero training loss, but still generalize as well. And the risk continues to decrease as model complexity grows. And training data interpolated exactly down to near zero training loss. And the empirical relationship between overparameterization and risk appears to be robust across many data sets and different model families. So in this particular paper, that's by now quite well cited by Belkin, Daniel Shu, and so on, they have demonstrated that this kind of phenomena exists for MNIST, CIFAR, some other data set, and the speech data set TMIT across random Fourier features, random forests, neural nets, and so on and so forth. And people have observed this like repeatedly also in slightly less toy data sets. Right? In fact, then people in the community, there has also been discussions on whether this is a new finding or not. Turns out it's not. There's a brief sort of commentary on this. And the theory behind overparameterized machine learning is evolving, and this is one of the recent survey papers. So the phenomena is double descent is, I would call it a schematic. In terms of, depend on the application domain, data set, and so on. You might also see not a double descent, but single descent, such as in computer vision. The ResNet paper basically showed that the risk and empirical risk keeps decreasing together for a long while. And sometimes we see multiple bumps too. There are more nuance to this, right? So we could try and measure basically the ability the large networks is able to overfit or learn arbitrary things, essentially, that are essentially. Here, there's an experiment conducted on what's called a CFA10 image classification task. And here's a picture of CFA10. It's basically little pictures of 10 different object classes that are fairly distinct, and the objects are front and center in the. Right. So in this toy case, people have trained neural network with random labels. The advantage of that is that in this key equation that we are staring at, the true risk is actually known. If I randomly permute the label on this balanced 10-class data set, the true risk or correct classification rate is 1/10. I'm just random guessing. And the training error is turned out that it's being driven to 0, even with random labels with this red curve. Obviously overfits because it's just learning noise. And when we increase the fraction of random labels, the test error sort of converges to where we expect it to be, like 90% test error. What this shows is that if you invest lots of effort in optimizing your model and doing your gradient descent right, it may not reveal insights of the nature of the generalization. So even if I drive my empirical risk to 0, it may not be learning meaningful things, right? Right, here's a picture of inception. For those of you who don't know, I don't like that, I suppose. And you say, what about other usual tricks that we're talking about and other classes have been talking about? What about regularization, L2 regularization, and data augmentation? So these are quite frequently used, right, in practice. So again, on CIFAR, the authors of this chapter have presented an experiment of a inception model that has 1.6 million parameters, and they basically turned random cropping and L2 regularization on and off. The training accuracy is always 100%, and then the test accuracy, right? So if we build from the base, which is no regularization and no data augmentation, is 85% accuracy. That's a generalization accuracy. But if we turn both of them on, it's only growing to 89%, not by that much. Meaning regularizations do help, but it's not the main ingredient, or seems to be not the main ingredient for strong generalization. It may not even be necessary. You have a large model, yeah, just learning. So how do we think about how learning works at all? And how do we think about delta gen, which is like, how do delta gen behave? So this chapter presents 4 different views on how we formally characterize delta gen. In today's session, we're going to cover the first one in some detail. We're going to briefly mention the model complexity one. And then the other 2, we're just going to sweep under the carpet and show you a scary formula. Yeah, you're welcome to ask questions, right? So the thing to note, then, the reason that I'm showing you there are 4 different views is that they all arrive at similar result, that the upper bound on delta gen of classifier depend on n, and it decreases as n increases, which is good news, right? That's when we have more data we're learning. And the complexity of ideal predictor. So as if we learn more complex predictor classes, the upper bound on delta gen also increases. It doesn't mean we don't, like, a smaller delta gen is better. But as we learn more complex predictor classes, the upper bound for delta gen is larger. It's not guaranteed to be small, but it can practically still be small. So what we are also hoping to get through to you in this section is that generalization is a multifaceted object. Then when you want to get better generalization performance, we all do, right? When we try to use machine learning, it's useful to think about these different aspects, like model classes, optimization, like generalization guarantees. So this is, yeah, one of the thought processes that will drill you towards these, right? Okay, so here's I guess the beginning of the real messy part. Let's first think about how do we expect delta gen to scale. And we think about it using what we learned in probability 101, central limit theorem. Right. So for a fixed predicting function f with infinite amount of data, the expectation of empirical risk should be equal to population risk. So this is the informal statement. I'm not going to read you the central limit theorem again, but basically with lots and lots of data, delta gen shrink to 0. All right. But with finite amount of data, let's say size n, we want to upper bound delta gen. Right. And the style of this upper bound is as follows. We want it to be small with high probability. Because the data set we obtain are random samples from like a true distribution, we cannot obtain analytical upper bound that's not probabilistic, right? So this style of upper bound sometimes is like being called as an epsilon delta bound, which means it's in either of these 2 versions, as you will see. The first version is that the generalization gap being bigger than epsilon, the probability of that being bigger than epsilon is less than delta. So the intuition for epsilon and delta are that they are both small constants. What counts as small is tricky, but just, yeah, small. And then the other version is that the probability of delta gen, or absolute value of delta gen, being less or equal than epsilon is at least 1 minus delta. All right. we'll see picture of this, like, or pictures that look like this in a few slides. But the question we would want to be asking, given this epsilon delta like style bounds, is how fast does delta gen shrink with respect to a number of data points n? Right, so roughly speaking, you will want something like delta gen shrinks as like a function of, let's say it could be 1 over n, or it could be 1 over root of n, or 1 over log of n, 1 over whatever, let's say n to the, like, or 1 over k to the power of n, right? So which one among these different options is the best if you can obtain? Let me just ask people in the room. You want, like, for the same amount of data, you want, like, yeah, delta gen to shrink fast. So this is sort of the opposite as our algorithm class. If your algorithm runs in log n, that's super good. Actually, log n is the worst, right? Right, so, yeah, but no, we don't get that, right? The spoiler for this lecture is we get 1 over root. Right. So that's basically the expectation we have for the rest of this session. Yang Wang was asking online. So the overparametric problem is the problem behind the overfitting phenomenon. That's on the chat. Let me briefly clarify. Actually, the overparameterized model, it used to be thought of as a problem. Like when I started first learning machine learning, it was early 2000s, and at that time, neural network was believed to be prone to overfitting and not do as well as things like SVM. That's because we haven't overfitted or overparameterized it enough. The last 10 years, we've shown this to be not a problem. So it basically, yeah, the idea of overparameterized models completely changed what people think about overfitting. Yeah. It seems to be quite general. Right, so if you read, like, I didn't paste the paper, like, graph from this paper, this paper, right. It basically, right, it has one theory, and then the empirical result included not just neural network, but also random feature regression, random Fourier feature regression, and also random forest and a number of other models over a variety of different data sets from images to speech. So, right, if we have lots of data, over-parameterized models seem to be a good idea. If you have like only a small amount of data, let's say 20 data points, and you still want to learn, so sure, that's still a good idea in a lot of cases. So yes, we were here, and we were just talking about how fast delta gen shrinks. Now, before we actually talk about the bounds, I need to hit you with 3 inequalities. Some of them you might have seen, some of them you may not. So here's, right. Sometimes they're called concentration inequalities. Some computer science programs cover them as a sort of in the foundations class. If you have taken probability, you might have seen them. But anyway, just you have seen them, then you can take a nap for 5 minutes and come back. The first one is Markup inequality. Let Z be a non-negative random variable. There's no other constraint to Z other than it being positive. Then we can essentially upper bound the probability of z greater than a value with expected value of z over t. This is rather counterintuitive at first sight, especially if you've seen it first time. But to prove it, actually quite simple. So this is for the discrete case. For the continuous case, replace the sum with integrals. Basically, we define E of x as a weighted sum of the values like the variable can take. And then we first upper bound it by throwing away the values going from 0 to j. And then we replace, actually, I think this should be t. And then we replace every xi here that's greater or equal to t with t, right? And then, right, so this will become this part. The sum over these probabilities, t comes outside and get divided and goes to the other side because it's constant. Right. T is a value. Oh. Right, yeah. Yeah, so basically, yeah, so xj equals to t. Right. Right. So let's look at an example. If we have a weighted coin with probability of landing heads is 20%, which is quite low. Right. And then we will want to bound the probability of landing heads 16 times out of 20, which is quite far away from its expected value. Right, so we'll use Markup inequality to do so, and then we'll use the next inequality to do the same thing. So we can compute E of x, right? So remember that our bound was of the style E of z, right, over t, right? So we first compute E of x, and then t is this value of the random variable, right? And therefore, this is the bound, and it's 1 or like a quarter. So meaning that, well, without any, so in this inequality, we only know the random variable is non-negative, and we only know the expectation. And well, you all know combinatorics. You can do the actual probability in this case. The bound is very loose, quite far away from the actual probability of having 16 heads of such a biased coin. But we have a bound nonetheless. We can right away, we only need to know E of x and the value, then we know it's not going to be half, not going to be 3/4. So the next one, Chebyshev inequality. We now know a bit more about the random variable. We know E of z, or mu sub z, and we also know its variance, sigma square of z. We still have this random variable value t in this inequality. What this says is that the probability of random variable z that are at least t like deviation from the mean is no more than sigma squared over t squared. Right, so if we apply, a lot of times this random variable z we're looking at can be the mean over a data set of size n. Apply central limits. Yeah, so What this says is that the probability of being far away from the true mean is bounded by this quantity that scales inversely with n. Okay. And the picture for this kind of bound, or the picture for epsilon delta kind of bound, is as follows, right? The probability of landing up in the blue region is no more than hopefully some small probability, right? So the way to show this Chebyshev inequality, which is just written again, is by using Markup inequality. So we want to show the first line. We square both sides. And plug in Markup inequality the right hand side. And because expectation of x minus e of x squared is variance of x, we get the Chebyshev inequality. So how does this do on the weighted coin example? So we already computed e of x, we now compute variance of x, which is 3.2. And then we plug in the same into Chebyshev inequality, we get a better bound, which is 1/45. Still pretty far from the true probability, which is 10 to the minus 8. So moving on, these are preludes or prereqs. Housekeeping inequality is going to be used a lot in the rest of this material. It uses yet some more information, which is it requires the random variable to be bounded. So if we have independent random samples, each of them is bounded. And if we try to bound mu the sample mean, then it's bounded by this, essentially. Exponential probability scaling with n squared. One special case that's used a lot is the following. If we plug in basically the bound to be between 0 and 1 for all of the random samples in Z, we get the probability of sample mean deviating from the true mean more than t is not more than exponential of minus 2nt squared. So let's just translate this back to the epsilon delta language we have, right? So with probability at least 1 minus delta, the difference between mu and mu z is less than epsilon. Here's the two-sided version or one-sided version of this. So if mu hat can be both larger and smaller than mu z, the two-sided version is basically the delta, or 1 minus delta is 1 minus 2 times the bound on the right-hand side. If we know that mu hat is larger than mu z, we can argue this is the case with empirical risk and true risk, then it's just 1 minus 1 times x. The general advice is to use the two-sided, which is more general. All right, so how do we use Housekeeping inequality? So if we know a person's height is between 0 and 9 feet, this is American text, right? The units are weird. Anyway, 9 feet is what? 2 meters and 70, roughly. No one is really taller than that. And if we sample 30,000 individuals randomly, using Housekeeping inequality, we can know that with 83% of probability, the sample mean should be within 1 inch or 1/12 of a foot of the true mean. So this is, I think, one concrete example of having lots of data is guaranteed to give us useful information. And as n increases, I guess the probability also increases. Yeah, read it slightly differently. So if the random variables have low variance, tightly bounded, then small experiments will quickly reveal insights about the population. So the mention of low variance is due to Markup inequality. Variance is on the top, on the numerator of the bound. And then if population has large variance or effectively unbounded, then we need lots of data. So in that case, it doesn't say that we shouldn't do any learning until we have lots of data. It may say that our estimators and algorithms and predictions may need to be resolved. Maybe we want to use a simpler model family or many of the other nodes in the machine learning system that we can tweak. So here's another direct use of these inequalities that's important. Going back to generalization gap after 10 minutes, there are, let's just say, two empirical schemes. One is the empirical risk is large or training error is non-trivial. The generalization gap decreases at 1 over root of n. And the next slide covers when training error gets driven down to 0, what happens. So if we consider a single prediction function, so this bit is a bit counterintuitive. The function is fixed but chosen independently of the sample S. So it's not actually guaranteed to learn anything. But it's also not a random predict. So if we just apply Housekeeping's inequality, so up here it's just written with epsilon in it, but the t. So with probability 1 minus delta, the book says we can upper bound delta gen of f log of 1 over delta over 2n square root. The bound that's more often technically used is the one below, which is a bit different than the bound in the book. Or in a book chapter, is to use the two-sided of things. We get a looser bound, right? So there's an extra 2 in here. And then we again relax this bound, realizing delta is small, right? Delta is likely to be smaller than a half. Otherwise, it's not too meaningful to say with probability 1 minus delta. Then we basically get, with probability 1 minus delta, we get a delta gen is less than log over inverse of delta over n taken as square root. Right, this is the first scaling regime. The second scaling regime is when basically training error is, let's say, almost 0. Then the reasoning is slightly different. Right? We argue that, right, suppose the generalization error is non-zero and it's larger than some small epsilon, then the probability we observe training error equals to 0 cannot exceed, essentially this is a binomial problem, of all the probability on all training data, the loss is 0. In order for empirical risk to be 0, then the risk on every single data point needs to be 0. And that's where this comes from. And then take the limit of n goes to infinity, use our calculus, we get this, right? And then we log both sides, we get this bound. So the difference between this bound and the bound on the last page is the absence of square root. In the overparameterized or when training error is close to 0, the generalization error shrinks faster. Good news. Yes. Oh, you mean here? Yeah, this is due to right. So in a lot of these bounds, constants get thrown away when we have a nicer looking looser bound. So what I have argued on the slide is that this last one is a looser bound than this one because if we can write this as essentially 2n, right? And then log of 1 over delta plus log of 1 over delta. That's basically multiplying 2 on both the top and bottom. Yeah, and then I can write this as log of 2 plus log of 1 over delta on the top. Right, and then I compare these two terms. So if you work in ML theory, in this particular area, what's important is the rate. It's whether it's big O 1 over root of n or big O 1 over n or something else, or one of like big O of log n over n, as we will see. The constants seem to be not very important. Another thing that we've been sweeping under the carpet is that sometimes if we plug in like real numbers of n and delta and so on, sometimes these bounds are like very big. And they may not make sort of empirical sense, but they help us reason about the rate at which delta gen is shrinking. Okay. Yeah, so there's a question online. I'm gonna try and address in real time. Let's see. Qinyu asks, does it mean that if we have extremely big models such as empirical risk driven to 0, then we'll have better performance than any current model? Because generalization gap will also decrease. Does this mean the future of AI are very big models? Yeah, okay, so we only talk about over big models and empirical risk being 0 in like empirically, right? Empirically, if you have lots of data, the empirical risk will get driven to 0 by very big models. But if you don't have lots of data in limited hypothesis class, you probably don't want really big models. And there's a whole suite of other questions about whether you trust your big model, whether you can interpret it, and so on. Yes, there's lots of hype and concerns about things like GPT-3. Yeah, let's cover the 101 of learning first, and then we can, if there's time left, we can chit chat about any of these or throughout the class. All right, so we've covered 2 scaling regimes and 3 inequalities. Now let's talk about algorithm stability. What does it mean, right? So what algorithm stability tries to measure is basically whether models are sensitive to perturbations in the data. Meaning, if I swap one example out, what is the most worst case in terms of risk and delta gen? Right. So specifically, how sensitive an algorithm is to change in a single training example. So what we covered, there are many ways of exactly quantifying algorithm stability. We sample a single data point, leave one data point out, which are quite different. And then we can also arbitrarily corrupt one single data point, which would be adversarial if you think about it. We're only going to talk about the first. Some more notations. We already saw this if S refers to a data sample of n points, x, y as a tuple. Now we call the tuple x comma y z. Don't ask me why. The book wants to do it. It's reasonable as well. And we write the loss function as a shorthand in one of the many ways where we just write f comma z or f bracket s comma y and so on. Right. So what's new here is how do we represent a correct or replaced resampled single data example? So basically, in this S superscript I, we replace the I's example with Z prime. Note that both Z and Z prime actually are assumed to be from the same distribution, which is the joint of XY still. So we can imagine we can have two separate data samples from the same distribution, know them as S and S prime, and this S superscript I is just the I's example from the S prime got swapped with the, or was replaced from the corresponding example of S prime. All right, it's a mouthful. And now here's the new notation, a learning algorithm rather than a predictor A maps from the space of n data samples to the space of function f, or we used to know this as curly f. Right? And this learning algorithm A is assumed to minimize empirical risk. Later on in this chapter, there were talks about optimization, but for now, let's just assume this. So there are two definitions that we'll go through, and then we'll get to a bound. The first definition is called the average stability of an algorithm. It measures essentially the loss of the algorithm A trained on the original data set versus the loss of the same algorithm A trained with a slightly different data set with one data point replaced. Right. And the loss is measured on this test sample or unseen sample Z prime. And we average this value over by replacing every single data point in the data set. That's here. And the expectation is taken over all pairs of data sets. So the high level interpretation of this average stability measure, let's call it delta A, is that it measures the change with respect to one training example, also measures the change with respect to seen examples and unseen examples. So note it's a little bit of a cheeky notation here. So this Z prime, it's sort of unseen. We can think of it as test example, but it can also be like the change in the training set. The proposition, yes. Yes. Yeah, let me do this. So actually, so this is measuring training loss, and the left-hand side loss term is measuring test loss. Yeah, thanks for the question. And the proof, right? Okay, let me state the conclusion. So basically, the expected generalization gap equals this average stability, which is kind of good news. So we have now written out a delta gen that actually has functions in it that we can compute and has summations over a data set that we can actually run. The proof basically involves reasoning about whether that prime is training or testing and so on. You can go through that. It's not too long. All right, so for now, we view delta A as sort of version of computable delta J. The second definition we want to go through is uniform stability. The word uniform in math a lot of times refer to the worst case. Is the case, right? So the comparing what we just defined in average stability to this uniform stability, it's basically replacing the sum and expectation with two soups. Where soup is basically maximum that's not necessarily in the set. Right, the first supremum is taken over all possible z's, basically all possible data samples. The second supremum is taken over essentially all possible data sets. So these are corresponding measures. And moreover, the little z right now is not assumed to be from either of the data set, but it's sampled from the same distribution. So this captures the worst case difference in the prediction of the learning algorithm run on two arbitrary data sets that differ exactly by 1 point. So this is called uniform stability because it holds for every algorithm A and the entire distribution X, Y. So I won't prove it here, but this is a rather important conclusion. Basically, this uniform stability of an algorithm, or the delta soup of A, upper bounds average stability, and therefore upper bounds the delta J. Here's another quick prelude before we get to the bound. We've talked about convex functions at least twice in this class, and you may have seen it elsewhere. It basically refers to these ball-like functions that were, like if you connect any 2 points in a function, the line sits above the function itself, and well, you can do downhill skiing on it, and you end up in the minimum, right? So there are two related concepts. The first one is called strictly convex functions, where you replace the larger equal to or smaller equal to a strictly smaller sign. There's the second concept that's related. It's called strongly convex functions. So one notable property of convex functions is that the entire function sits above, let's say, the tangent, which is a line of that function at any given point, right? So the entire function sits to the above this tangent and that tangent, which is this equation is trying to say. For strongly convex functions, the entire function sits not only above the tangent, but also it's lower bounded by another quadratic function. With basically, there exists a mu, constant mu greater than 0, where this quadratic function sits entirely below the function. The top part we'll talk about in the next slide. So this kind of function has nice properties. Strongly, so as you can see, the basically convex functions contain strictly convex functions, which in turn contain strongly convex functions. For example, x squared, like among these functions, like x to the power of 4, right? So this is convex, but not strictly convex because it's a line, so therefore there's an equal sign. And this one is not strongly convex, but it is strictly convex. as you can imagine, right? So extra power 4 is a ball-like function, so it's strictly convex. It's not, there's no point of E that's flat, but it's not lower and upper bounded by quadratic functions because it's higher order polynomial. Right? So the nice properties of strongly convex functions, said in a high and wavy way, there is a unique global minimum, which is also true for strict functions, but it's also fast to find. There are nice rates on gradient descent that we're not going to. So in order to bound delta soup of A, we now need two assumptions. The first assumption is that the loss function is differentiable and strongly convex, as is possible loss functions, and also that the loss function is L Lipschitz for every single data point. What does that mean? It means that the gradient, the volume or the magnitude of the gradient vector of the loss function is bounded by this big L. Or basically the change in the loss function across two different parameter values, W and W prime, is never bigger than L times the difference of the normal parameter points. All right. Assume these nice conditions. Here's the bar. Yeah, the theorem begins by stating these assumptions. Then the empirical risk minimization satisfies, which is ERM is then treated as an algorithm A, right? So delta soup of ERM scales quadratically with, like the bound, the upper bound scales quadratically with L, and scales inverse proportional to N. Okay, so this is not too bad, right? The proof of this is also not too onerous. It requires a few steps to convert the goal of the proof and then work the other way from the loss function side, the delta soup side, right? There is no explicit reference to what kind of model class are we talking about, but there are implicit constraints, right? So mu strongly convex function that's also L Lipschitz means, for example, square loss is in this class, but and a number of other things we will see, but maybe not much else. So if you are wondering what kind of loss functions are strongly convex, you can go read this Figaro mass stack exchange. So basically square, log, and a number of others. There is a recipe to generate strongly convex loss functions as well, which may or may not be useful. So the next question, the next point we're trying to make in the same slide is, what about regularization? Right, so you say there are good news and slightly bad. Right, the good news is the properties of strongly convex functions dictate that if I take the sum of a convex function, convex loss function, and an L2 regularizer, which is strongly convex, the combined result, this regularized loss, is actually strongly convex. Right? And now we need to make some more assumptions, or reasonable assumptions actually. Once we regularize the magnitude of the parameters, we can assume that the parameter sits within some L2 ball in this case. We have seen different forms of regularizers. They usually sit within some norm ball. So we assume that the B is the size of the norm ball. And we can now set the regularizer term according to L, the Lipschitz constant, and B and N. We can then, which then leads to an upper bound in the regularization term, which shrinks according to square root of N, which is good because we know that in a lot of cases we can make the loss quite small. Now the regularized loss is also going to be nice. And using this expression above, we can then bound generalization gap to be also order of LB over square root of n. So with regularization, we can now turn non-strongly convex losses into strongly convex loss, but the rate of convergence here is a bit slower. It's 1 over root of n rather than 1 over. So that is what I need to say about like algorithm stability. Now let's switch gears to model complexity and check if there are any more questions. Like Alex Sohn answered the last question. And this will be I think the last slide of technical content, and afterwards we're going to see, and this is pretty much it. So we would like to reason about model complexity. So for now, let's just intuitively think of them as how many different models we can have in a model class. You say, well, in regression and many other things we work with, it's infinite. Let's assume they are finite for now. Infinite there's a recipe in the next few pages that we're not going to be able to cover in depth. Let's assume that, okay, so little f is in some function class, and then this is the number of models, the norm of like cardinality of the function class. We can actually obtain that. All right. So the stuff in the green box is what we've seen before, the Housekeeping inequality and the data independent predictor, the bound on data independent prediction functions. Note that we use the two-sided relaxed version without the two at the bottom. The claim is we know model complexity characterized by the cardinality of curly F. The bound, upper bound on delta gen with probability 1 delta is actually log of cardinality of F plus this part. What is it actually says? And two logs together. The top is actually this, right? So it's the cut of F times 1 over delta. Why this is the case is this bound on the upper right-hand side is from a data independent, pretty much arbitrary prediction function F. In order to bound the probability of delta gen being non-trivial for all little f in big F, we apply the union bound. Basically, the worst thing that could happen is that each of the models in the class is at the bound, right? So sum over n. Small f, like this. going to use a notation that's a bit loose here. So the probability of all the models in the class have a large data gen is less than each of the model have a large gen. So the takeaway from this particular page is that the cardinality bound is a basic measure of complexity, and this functional form of complexity over n taken as square root appears in a lot of places. So to answer your question about, oh, what if the cardinality of curly f is infinite? There's a number of measures for infinite function classes. One of the well-known ones is called the VC dimension. Stands for Vapnik-Chovnetsky's. Vapnik was one of he laid the foundation for SVMs. So what it does is to essentially count the size of the set which the function class can induce all possible labelings. That is a mouthful. One example of that is linear models of a d-dimensional space have a VC dimension of d. It is the same as number of model parameters. And if we plug in VC dimension into the bound, we get a slower rate. Basically, the VC dimension of curly f comes here, replacing the cardinality of f. But overall, this is a slower bound because of the log of n. The good thing about VC dimensions, hyperplanes with bounded norm, the VC bound becomes something like this, meaning that it does not depend on the number of input data dimensions. This was one of the principal reasons to use support vector machines. So at that time, the theory actually came together with the practice of training support vector machines, like essentially non-bounded hyperplanes and data, like unbounded data, which has nice guarantees. So these are just, I guess, cultural exposure so far. I'm not expecting people to sort of derive these. The derivation of this particular thing is also not in the book chapter. All right. Here is the slide that dumps all like equations you have seen and you have not seen on it. Basically, in terms of bounding generalization risks, we know the uniform bounds, upper bounds, the average stability point bound, empirical risk minimization, basically scale with respect to L square over n. We've also looked at an expression with model classes, which I think is helpful to know. And the other two, we just look at them. I haven't even defined for you what is this calligraphy R, which is Rademacher complexity. But they basically have a similar form, right? The last one is interesting. Bounds how much error you get in the process of doing SGD, rather than like at the end of the learning, assume we have minimized empirical risk, what happens? That's pretty much like, as I said, the bias-sized exposure to generalization and the ways to thinking about bounds. All I have to say for this time. We pause and taking what we have learned. We looked at the notion of generalization gap. We looked at overparameterization as an empirical phenomenon. We looked at the three inequalities and what it meant in terms of the two scaling regimes. We talked about 1 over n versus 1 over root of n. And we looked at a little bit of theory of generalization. the stuff that's grayed out, we didn't even really look at. Okay. Some questions, if people have any. Chat, basically. Alex Owen is answering a bunch of. Reiterate. In terms of thinking about bounds, there are many different factors that will affect these, such as the model class, whether we can find the optimal F, as we will say, cover in the next Monday's neural network, right? Like neural network is basically a not identifiable model. There's like exponentially many models that will have the same loss value. Just think about if we just permute, if we call the first neuron the second neuron, and so on and so forth. So there are exponential many functions. And we have always assumed that the training test data are sampled from the same distribution. In practice, that may not be. Things have drifted. There is a holiday coming in, like customer behavior completely changed. There might be penalty terms accounting for distribution shift, which I do not know how to formally characterize on the spot. I hope this helps. This is the first time I think we covered generation. There's a question? Yeah.
Cover the increased rates of the gene on the offending line.
Good question. Let's go back there. Yeah, okay. This is the whole thing.
Increased rates of gene is
right, so Hopkins captures, I guess, N as the main driving factor. And the actual bound we saw, right, such as this one, it involves L and mu because it affects the amount of deviation T in Hopkins. Yeah, if we can get them all on the same page. Basically, in Hopkins, we have something like x minus 2 n t squared. Is that right? Or n squared t squared. Yeah, 2n t squared or epsilon squared. Go back there. Just gonna call it epsilon because it's epsilon many places. So P of the gen. This.
the matter how we sample from a large size and the branch the rates never change. For example, if we sample the students from a big class, small class, the decrease rate is never changed, right?
That's a good question, right? So we always, as Alex was also answering online, we always assume throughout this lecture, we assume there's x comma y, they are sampled from some distribution that's fixed. And we train from it, we try and generalize on it. In reality, you might train on students from a big class and try and do a prediction on a small class that will not work as well. Is that the question, or are you asking about something else? And we are also assuming that we can potentially get infinite amount of samples from.
I think the truth is that the inside is
Oh yeah, in reality, we always learn and test on finite sample sizes. So yeah, so therefore, these tells us how fast delta gen shrinks. Like there are many empirical results where we can vary n. Sometimes we can even generate data. We can use synthetic data to verify these bounds very sensibly. Even for real data, we can just resample the data and verify the rate at which it shrinks, which is very important because it may not seem that important for a batch learning setting where we are usually working with a data dump and trying to learn from. But for an online or active learning setting where we're trying to, or reinforcement learning for that matter, we're trying to take action. So trying to see, like acquire the next sample. So in a bandit setting, we're essentially trying to, let's say, if we have a number of gambling machines and we're trying to maximize our profit, but the machines like returns are unknown but fixed. In that case, the number of samples really matter. A rate of convergence of, say, root of n meaning we versus 1 over n, then the one that's linear. Inversely proportion to n means that we can gamble like a lot less times than otherwise. So there's lots of literature on online learning and rates and so on that we're not going to touch. We are trying to design an assignment question next to actually get people to have some like working idea of this. We'll see if we find a setting where it works. Yes. Yep. Yep. Wait a sec. Let me go there. Yeah, the capital. So the capital Z is a random variable, which is essentially x, y, tuple. The little z is a sample. Or there. So what is the proper expression of that? So when we learn probability, we always write something like yes. Good question. Let's go back there and have another look. That one. Yeah, so here, A of S, the output of that is it's actually F, like a classifier. Yeah. Right, so the loss notation here, it says, right, this is them abusing notation. The loss of f on one example. Yes, notations are tricky. Once we venture outside of the usual textbook we read, it takes a while to wrap our heads around. Doesn't quite help when they also abuse it a bit. Convenience. Yes, it takes a while to get used to the